Hi guys, we are continuing to talk about gases. So let's review some properties of gases that you probably know from maybe elementary school or middle school. So gases expand to fill the volume of their container. They have no definite volume, and so they're expandable. So because they're expandable, they're also compressible because of the large spaces between their particles. They take the shape of the container as well as the volume of the container, like we've mentioned. And gas particles flow and also they diffuse. The difference between flowing and diffusion, flow usually means from one direction to another, and diffusion means it's a random motion, so it goes in all directions. But gas particles will flow and they will also diffuse. So if I were to take a container that has CO2, for example, carbon dioxide gas, and pour it, it will actually pour because it's more dense than air, so it will flow down. If I were to spray perfume, it's going to diffuse in all directions, so it also diffuses, so it does both. So let's say you have a container that has a gas in it. What variables can you measure for that gas? So you can measure temperature, volume, amount, or pressure. So let's start with temperature. Temperature, of course, you use a thermometer to measure it. And it gets the capital T as its symbol. And we can measure it in Fahrenheit, Celsius, or Kelvin. These are the three units. For temperature, Fahrenheit and Celsius, we say degrees Fahrenheit or degrees Celsius. With Kelvin, we just say kelvins, no degrees. So your thermometers can be in any of these. Usually around our science room, they're in Celsius. But when we do calculations in this chapter, we have to use Kelvin. The reason is our calculations, we're going to relate to these four variables. And so if we have a negative temperature, that could make us calculate a negative volume or a negative pressure and a negative amount. And that doesn't really make any sense. And so we have to use the Kelvin scale. So if you're given any temperatures that are not in Kelvin, you have to convert them to Kelvin first. To go to Kelvin from Celsius, you add 273. To go from Kelvin to Celsius, you subtract 273. Now, it's really hard for me to remember when do I add, when do I subtract. I just know Kelvin is always positive, so Kelvin is always the bigger number. So when I'm going to Kelvin, I add. When I'm going away from Kelvin, I subtract. Next is volume. Capital V is the symbol for volume. And if we had a container that had a gas and we wanted to measure the volume of that container, usually we use water displacement in a graduated cylinder. So what you would do is you would take that flask or that container, fill it up with water, and then pour that water into a graduated cylinder, and the volume of the water would be the volume of the gas that was in that container, because the gas will expand to fill the volume of your container. You can measure volume in any units that you would like. You could use liters, cubic centimeters, cubic decimeters, gallons, quarts, anything that you want, cubic inches, really any unit that you want. Next is amount. Amount gets lowercase n, and it stands for number of moles. And as you can see, it's measured in moles. Now, we don't have any molometers, and so we can't really measure moles directly, but we can calculate moles from the mass. So what we could do is we could mass our gas and then use the molar mass to convert to the number of moles. And then finally, pressure. Collisions between gas particles is what pressure is. Imagine somebody pounding on you. Those collisions cause pressure. And so those gas particles, because they're moving fast and they're moving randomly all the time, they're going crazy, they're hitting each other, they're hitting the walls of the container. Those collisions between the gas particles and the container, those are what pressure is. And so the more collisions there are, the more pressure. The less collisions there are, the less pressure. Now, pressure can be measured in a variety of different units. We have a few here. So this is standard pressure. So at sea level, what standard pressure is 1 atmosphere, 760 millimeters of mercury, 760 torr, or 101.3 kPa. These are numbers that you need to memorize. So let's talk about some of them. Atmospheres, which is ATM for short. This is a unit that they came up with so that the standard pressure is an easy number, and so they said, oh, it's just going to be 1. So 1 atmosphere is standard pressure. 760 millimeters of mercury. So mmHg stands for millimeters of mercury. That comes from barometers when they were made out of mercury. So Mrs. Hummel, who used to teach chemistry here, she was my mentor. She told me that about 25 years ago, what they would do is they would make a barometer in science class. So they would literally take a tub of mercury. So let me try to draw this for you. So imagine this is a tub full of mercury. And they take a eudiometer. A eudiometer is a very, very long, narrow tube that's graduated. So it looks like a graduated cylinder, but really, really, really long and thin. And they would fill it also with mercury, put their hand on top, and then flip it upside down into that tub of mercury. So it would look, and I apologize, I can't draw, kind of like that. And these are your graduations. So what would happen is most of the mercury would stay into the tube, but not all of it. So this is all mercury. And this is all mercury here. When they measured the height of this was 760 millimeters of mercury. Now, if you've ever played in the tub as a kid, if you've never tried it, try it. Maybe take a bath, or even in a sink, fill it with water, or fill your tub with water, and then get any empty container, like maybe an empty water bottle or an empty shampoo bottle or something like that. Fill it up with water and put your finger on it or your hand on it, and then flip it upside down into the water and let go of your hand. You'll find that most of the water stays in that container. Very little of it actually falls down. So what they found is that the same thing happens with the mercury. Most of it remains in that tube. Just a little bit of it falls down. And when there's normal pressure, the height, because it's graduated, the height that they can read is 760 millimeters of mercury. Now, why is that? Why does it stay? Why does the liquid stay in that tube? Why does the water stay in your, water bottle? Well, the reason is because of air pressure. So the gas particles in the air are colliding with each other. And they're pushing on everything. They're pushing on this, they're pushing on each other, they're pushing in every direction, including they are also pushing on this liquid right here. And that's causing the liquid to stay in the tube. And when there's normal collisions, that height is 760 millimeters of mercury. Now, what if you had more collisions than normal? So the pushing would be stronger, then it would push that liquid into the tube even more, and so the height would be higher than 760 millimeters of mercury. If there wasn't as much pushing, then it would be lower than 760 millimeters of mercury. So 760 millimeters of mercury is normal atmospheric pressure around sea level. So that's where that mmHg comes from. A millimeter of mercury is the same thing as a torr. This is named after an Italian scientist. They wanted to honor him, and so they named a unit after him, but a torr is the same exact thing as a millimeter of mercury, so it's equivalent. And then it's also equivalent to 101.3 kilopascals. kPa is kilopascal. Pa by itself without the K would be pascals. This is the same Pascal that made the Pascal triangle. They wanted to honor him again, and so they named a unit after him. So normal atmospheric pressure around sea level is 101.3 kPa. And again, atmospheric pressure or any type of gas pressure is caused by these collisions between the gas particles and the walls of the container. You're probably, if you drive, have checked your tire pressure at some point. And usually the tire pressure is in PSI, pounds per square inch. Each tire is different, but most tires need to be at a pressure of somewhere between 30 to 35 PSI or so. That's another unit of pressure. We usually use that, in America. We don't really use the English system. Some other places are in science, and so it's another unit of pressure. Atmospheric pressure, normal pressure would be 14.7 pounds per square inch. That's not a number that you need to know. That's just for your reference. But these 3 numbers here, you do need to know those. Now, just so that you have a reference for what this means, I've drawn on my hand right here about a square inch. So we're saying that there's 14.7 pounds per square inch of pressure on you from the atmosphere, from normal atmospheric pressure. That means that for every square inch of your body, you have almost 15 pounds pushing on you from each direction. That's a lot of pressure. Now, we don't feel that because we're used to it. You know, from the moment we're born, we're exposed to that atmospheric pressure, and so this is normal to us. We only feel differences. So if we go on top of a mountain at high altitudes where there's lower atmospheric pressure, then we'd feel it. Or if we go on the bottom of a sea, in the sea, under the sea, then there's higher pressure, and so we'd feel that. If you go on an airplane, you feel the difference in pressure. But normal pressure is 14.7 pounds for every square inch of your body. That's a lot. So usually to demonstrate that, I'm not going to do it on video, but hopefully next time I see you in class, I have a bed of nails that a couple of my students had made for me for a final project, some of my former students. And so if I were to step on that bed of nails with my foot, which I don't do, I would get hurt, right? Because I don't have very many square inches in my feet. So, you know, nothing would lift me up, and I would just, because of gravity, fall into the nails and hurt myself. But if I were to lay flat with my back on the bed of nails, I would actually not get hurt because I have many, many square inches on my back. And if I was able to lay flat on my back, then I have a lot of square inches, and for every square inch, I have 15 pounds of pressure pushing me in all directions, including up. So if I can have enough square inches so that I have enough pounds of pressure to push my weight up so I don't sink because of gravity, I would not get hurt from my bed of nails. It's pretty cool. Air pressure is very, very, very strong. Okay, I do want to show you this here. This is called a manometer. So what we use to measure atmospheric pressure is called a barometer. What we use to measure gas pressure in general is called a manometer. So a barometer is a type of manometer. Barometer is specifically for atmospheric pressure. Manometer is for any gas pressure. So if you look at this, if we wanted to measure the pressure of a gas, what we do is we put it in some kind of container here, and we connect it to a YouTube. This is called a YouTube, not the YouTube like video website, but this is a tube that looks like a U, so they call it YouTube. And in there you put mercury or any dense liquid, and you expose it to the air, and you should know what the atmospheric pressure is. And these tubes are graduated, so you have the height of the mercury. And if you look at this, you'll see that the gas particles here are going to collide together. They're pushing on everything, on each other, on the walls of the container, and they're also pushing on this liquid. Same thing with the atmosphere here. Those gas particles are pushing on everything, including on this liquid. Well, who's pushing more? Looks like the air is stronger. It's pushing the liquid all the way down here, whereas the gas is only pushing it this much. And so that tells us that the gas pressure is lower than the atmospheric pressure. How much lower? By the difference in the height. So if we knew what the atmospheric pressure is, we can take that and subtract the height difference between them, and that's going to tell us the pressure of the gas. Let's look at this picture. So this is the opposite. So here my gas particles here are colliding, pushing on everything, including on this liquid. The gas particles in the air are also pushing on everything, including that liquid. Who's winning? Well, this time the gas is winning. It's pushing the liquid more. And so we know that the gas pressure is higher than the atmospheric pressure. How much higher? Well, it is higher by the difference of the height here. So if we wanted the pressure of the gas here, we would take the pressure of the atmosphere plus the difference in the height. So here we subtract, here we add, because we can tell that here the pressure of the gas is higher than the atmospheric pressure. Here we can tell that the pressure of the gas is lower than the atmospheric pressure. Okay, so that's a summary of the different variables. Now, you need to be able to convert between different units of these variables. So let's practice some of these. We'll start with temperature. So if I have Celsius, 22 Celsius is close to room temperature. If I wanted that in Kelvin, I'd add 273. So that would be 295 Kelvin. 37 Kelvin, that's very cold. If I wanted to take that to Celsius, I subtract 273. And so that is negative 236 Celsius. Let's look at volume units. So going from milliliters to liters. So if I had milliliters, I'd do a conversion factor. On the bottom, I put milliliters. On top, I put liters. 1 liter is 1,000 mils. And so it's 0.018 liters. Going from liters to centimeters cubed. I'm going to first go from liters to milliliters. 1 liter is 1,000 milliliters. And then I'll put milliliters here, centimeters cubed. And I know that 1 centimeter cubed is the same thing as a milliliter. And so I get 4,300 centimeters cubed. 500 centimeters cubed. Trying to get to milliliters. And so I know that 1 centimeter cubed is equivalent to 1 milliliter, so it's 500 milliliters. 2.2 decimeters cubed. A decimeter cubed is equivalent to a liter. And so 2.2 decimeters cubed is equivalent to 2.2 liters. Let's go to amount next. So going from grams to moles and moles to grams, I can use my molar mass. 2.8 grams of N2. Put grams on the bottom, moles on top. 1 mole of N2 is about 28.0 grams. Hopefully you can do that in your head. 0.10 moles. Going the other way around, 612 moles of SO3. Moles on the bottom, grams on top. 1 mole of SO3 is 80.1 grams. If you multiply 80.1 times 612, you get 49,000 grams. And we need 366, so we'll put a bar on that 0. Let's go to pressure units. So we know that 1 atm is equivalent to 760 millimeters of mercury, or torr, they're the same thing, which is equivalent to 101.3 kPa. So we have 22 kPa. We'll do a conversion factor. On the bottom, we'll put the same units so they cancel. On top, we'll put the units we want, so atm. So according to this, 1 atm is equivalent to 101.3 kPa. We get 0.22 atm. Next one, 289 millimeters of mercury. I'm going to put millimeters of mercury on the bottom. I'm going to put kPa on top. We know that 760 millimeters of mercury are equivalent to 101.3 kPa. Get 38.5 kPa. Next one, 4.3 atm. We want this in torr. So put atm on the bottom, torr on top. We know that 1 atm is equivalent to 760 torr. We get 3,300 torr. And the last one, 518 kPa. Put kPa on the bottom, millimeters of mercury on top. 101.3 kPa is equivalent to 760 millimeters of mercury. So we get 3,890 millimeters of mercury. Have a great day, guys.